All right, so what I'd like to do is write out the, F equals ma for a prototypical atom in our system so that I can, plug in our guess and look for phonon dispersions and all that stuff. But I first need to write out how am I going to write that? I need to write F equals ma. The MA part's pretty easy to do based on, the displacements that we've already written, but the F part's maybe not so obvious, or at least it's a little notation heavy. So let's go through that. So we're thinking about atoms as being bonded to one another, essentially via think about it as a spring force. These are harmonic forces we're talking about with phonons. So the way I'm going to write that is I'm going to essentially write this the same way I would write it for a linear spring, but I'm not going to use the letters that are associated with spring constant. So here's what I'm going to do. I'm going to write the force as a sum over essentially constants times a displacement, right? So, I think about, what we were doing in one dimension, and what we had said was that, let's say the force acting on a central atom had to do with the displacement of this atom, the displacement of the atom itself, plus the displacement of some other atom. They were connected by springs. And if I actually go and work it out, the net force acting on that central atom could be written as a linear combination of constants times, some linear coefficients times the displacements of the atoms from equilibrium. So that's all I'm doing here. The only difference is that now that I'm in 3 dimensions, there's a lot of different ways that this force can come up, right? So, well, first let me talk about which force I'm talking about. So the notation here, let me just remind you. So what I wrote here was F with a subscript I, and I have a K here and an L here. So what does that mean? That means the force acting on the kth atom of the lth unit cell in the I direction, where that direction can be x, y, or z. So that's what I mean by this over here, and all that this says is that the force acting on the kth atom has to do with interactions between the kth atom. Oh, missing a prime here. The kth atom, in the lth unit cell. That's the one this is the atom that we're actually interested in. It's the interaction with that one with atoms that are potentially in other places, right? So that might include the atom itself, but it also includes atoms that are a distance away. So they might be, if we're talking about in the 0th unit cell, those interactions might include atoms that are in the 0th unit cell, but it might also include ones that are like 1 or 2 unit cells away. And in principle, there's more than one atom in those unit cells, so I have to distinguish between which atoms are interacting with which. So these are essentially like spring constants that are associated with that. And then a spring, because let's say I'm talking about the force in this direction, well, if the spring is aligned in a different direction, then I might get components of that force that are along this direction, but I might also get some along this direction. So I need to distinguish about, whether, displacements of this atom are leading to forces in which directions. So in principle, these coupling coefficients have a lot of terms in them that we need to keep track of. So if it's not quite clear why I would write it this way, let me just come to that here. So why would I define the force constants this way? So why write it this way? It's basically because if you think about where force comes from in the spring constant sense, what we really mean is that the force constant should be derivable from the derivative of a potential, or the change in potential energy. So let me write this as the change in potential energy due to the displacement of atom, KL in the ith direction. That's what should lead to this force. And you can see that basically this implies that the potential energy associated with, or the change in potential energy associated with displacing atom I or KL in the ith direction works out to be half times the sum over, let's see if I can do this, k prime, l prime in the jth direction of u, I, I'm going to write it out and then I'll prove it. K, L, whatever those force constants were, so basically, the reason why it's written this way is because those are direct, like those forces are derivable from a potential, and you'll recognize this as basically a standard form of the potential energy. So you probably, if you took Mike Greenberg's class, or I shouldn't say Mike Greenberg, but it might be somebody else. Like if you took our Intro to Engineering Math class, you probably saw terms like this to describe the potential energy of spring networks. And so, essentially this is something like a half k times displacement squared kind of term, just written in the matrix sense. So if you work backwards from something like this, you get those type of force constants. And I should mention that these things, these size, these are called interatomic force constants. They're almost universally referred to that way in phonon literature. So these are interatomic force constants. And in fact, there are actually sort of canned software packages where if you have a particular crystal that you're interested in, you can actually simulate what these interatomic force constants are and sort of obtain them from first principles calculations for pretty much any crystal these days. So I'm not sure if I'll have a module for that in this class yet, but coming soon potentially. But I guess the bottom line is that these kind of things are typically known or obtainable, or you can see that the old school way of doing this is that you would obtain the dispersion relations first using experiments, and then you would work backwards to obtain the interatomic force constants that give you those dispersion relations. But the new school way of doing things is that you can actually determine these things from first principles, which allows you to calculate dispersion relationships without really having to do any experiments these days. So let's see. So the only thing I wanted to say was that, once, if these are the forces acting on things, then it's pretty simple to actually write out the governing equation. So, so I could write out Newton's law as F equals ma, so that's m, so the mass of the kth atom in the unit cell equals, so I'll just write this out for the kth atom in the lth unit cell. So that would be equal to the force acting on the kth atom in the lth unit cell in the ith direction. And so that's just given by these interatomic force constants summed over all of the possible combinations of interactions that you could have. With a minus sign. Boom. All right, so that's our governing equation. So now what we're going to do is we're basically just going to go ahead and plug in our, the form of the solution we were seeking, which, if I can squeeze it in here again, was u of in the ith direction for the kth atom of the lth unit cell was given by whatever's going on in the first unit cell times a factor that looks like e to the I q times a translation vector associated with that value of L minus omega t. So this is the solution we're seeking for the displacements. We plug that in and see what it gives us. So that's what I'm going to do next, and we'll see how that turns itself into a nice standard form eigenvalue problem. All right.